Hi, welcome to the next of our series of mini lectures, and in fact the last one for geometrical optics. We've been working on designing a zoom lens, and we've really done a lot. We've come up with some conceptual and mathematical model of light behaves. We've understand how lenses allow light to be bent and to collect the rays that come from an object to form an image. We understand what zoom lens does in terms of various mathematical models and are able to use ray matrices, ray tracing, and Gaussian optics to predict how a lens system is going to behave. We also know why the models don't predict the ideal performance of lens and aberrations, and today we're going to look at how we improve performance of an imaging system by putting in apertures or reducing effectively the size of lenses and images. And in order to understand this, it's best to go back and look at aberrations. Now, pretty much every optics book in the world talks about apertures before they talk about aberrations, but apertures and the terminology used for apertures really doesn't make sense unless you understand the aberrations. So just in review, we have third-order approximations where we basically expand a sine of theta into theta minus theta cubed over 3 factorial, and we define the amount of aberration by a term delta D that essentially says how big the deviation is from the real phase front, which is perpendicular to the rays, compared to the ideal spherical phase front of a perfect lens. And when you go through a whole lot of algebra that we haven't done, you find out that delta D can be expanded into terms of 5 different components, and each corresponds to one of the third order or Seidel aberrations. And the C terms on the front, we know, just depend on the particular imaging system. They're just constants. The first and most common type of aberration is spherical, and we know that varies as r to the 4th power, where r is how far out on a lens a ray hits, and h sub I to the 0 power. In other words, h sub I is not there at all because anything to the 0 power is 1, and h sub I is the height of the image. The second aberration is coma, going as r cubed and h to the 1st power, so it depends very much on the size of the lens and not so much on the image size. Astigmatism and field curvature have some cosine theta terms in there, but essentially they go as r squared and h sub I squared, so both the size of the lens and the size of the image play an equal role. In distortion, the final aberration depends only to the size of the lens to the 1st power, but the image size cubed. And if you go and look at apertures now, apertures can limit 2 things in a system. They can either limit the size of the image, in which case we call it a field stop, or they limit the size of an optic, or limit R, and that we call an aperture stop. An aperture simply cut down on aberrations at the expense of losing light in the system. So let's look at what we mean by a field stop first. If we have rays of light coming from an object that are imaged through a lens, a field stop, shown by the 2 black lines there, just limits the size of the image. Here the field stop is exactly set to the image size, which is not a bad thing to do in any kind of imaging system. An aperture stop, on the other hand, would go right in front of the lens, and it would limit the size of the lens so that not all rays of light will go through the system. And this is pretty much the explanation right out of your book, but let's go ahead and look at a couple other cases of aperture stops and field stops so we can clarify this idea. Here we have a 2-lens imaging system rather than the 1-lens imaging system shown above, and let's put in a field stop first. Here we put in a field stop on the intermediate image. A field stop doesn't have to go at the beginning of the system, at the object, or at the final image. A field stop can be put in anywhere in the system where there is an image. Let's go back and look at that again. Here we see our object, and the field stop, which we put in, simply cuts the head off of that arrow. It reduces the size of the image. Another way you can put in a field stop is by simply choosing a lens that's smaller than the image. In this case, if we put a 3rd lens in the system, again, notice we're cutting the head off that arrow again, and we put in a field stop by having a lens that's too small for the image we want to capture. An aperture stop, on the other hand, can go anywhere in the system as long as it limits the size of an object. There's an aperture stop after the 2nd lens. Or we can reduce the size of the 1st lens, for example, which is effectively an aperture stop because we're using a lens of a different diameter. Now, apertures have several effects on the system. At the bottom you see here an image that has some spherical aberration. This isn't a real image. This is actually a computer-generated image that I messed around with in some programs to give you an idea of what apertures are. And so real performance will vary from my simulation here. But if we go ahead and put in an aperture stop, let's see what happens. The image becomes much clearer because we've reduced the spherical aberration, but it's also much darker because, remember, the amount of light or the power we collect is proportional to the area of the lenses. And if we reduce the diameter of the lens by 2, we reduce the amount of optical power that goes through that lens by 4, so the image is darker after an aperture stop. If we put in a field stop, on the other hand, we don't do much to make the image less blurry. We've not really reduced the spherical aberration, but we would reduce distortion and some of the other aberrations. But notice that what we've done is we've put a black ring around this. We've cut off part of the image. We can no longer see it. And of course, aperture doesn't have to go in either as an aperture stop or a field stop. You can put it midway between where an aperture stop and a field stop would be. And the technical term for this is vignetting. Essentially, it serves as both an aperture stop and a field stop. You cut off some of the image and you improve the aberrations a little bit, and these things just look weird. It's generally not a good idea to do. So that gives you an overview of apertures, which is a very powerful technique for reducing aberrations in a system, and you simply choose the type of aperture depending on the types of aberrations you need to reduce.